Well, thanks, folks, for joining, and we'll get right into it. I think we're nearing the final stretch here on the hourly model, which is really exciting. A little bit more to do, as we'll discuss today. We're not quite there, but we want to give an update and get people's input. And I think today is somewhat important because I hope that in the next month, from this meeting to the next time we get to meet, that we'll be finalizing everything. So we'll start off today with just a recap of the last meeting, just to make sure that we have some overlap for folks who may be joining and weren't able to make the last meeting, and just remind us of where we're at. Then we're going to talk about an interpolation procedure that we've been testing and we feel is important based on how the model is formulated. And Travis will get into the details there. We will talk a little bit about example of how we can use supplemental data. And this is really exciting because I think you'll see how the model framework is more flexible. And we have a specific case where we want to use that flexibility, and we're just getting started on understanding like what this actually looks like, being able to model customers that have solar PV installed in the baseline period. And then we'll talk about hyperparameter optimization. Everybody's favorite topic. When you get down the home stretch like this, we've got to start figuring out, okay, what are these hyperparameters? How do they need to be tuned? And what do we want to set and establish for a finalized model? We did the same thing with the daily model, and we're entering that phase now in the hourly model. Then we'll talk about some population results. We're just starting to scratch the surface there. And that's where I think, what we see in the data sets that we've run so far will clue us into any performance issues. And that will show us where we need to maybe get back to the basics in some of the model formulation and hyperparameter tuning itself. And then we've got some next steps that I think are needed in order to wrap this whole thing up and finalize everything. So with that, we can go to the next slide. Just by way of a reminder for everyone, we've tested many different models in this working group for the hourly model. And a lot of these models have shown some promise in one way or another, but ultimately had some pretty significant limitations. We've even gone as far as to test a LSTM model and found that to be, expensive, and it even though it was a deep learning approach with high computational power, it just didn't actually perform much better when we looked at test data sets. So we found that to be overkill. We don't really see an enhancement in performance even when we're using state-of-the-art deep learning approach. But the current model that we have settled on is an elastic net. We've seen that this is more than 10 times faster than the Caltrack 2.0 model, that it's, that's really where we're trying to improve. And that we are now using new model inputs, including solar irradiance. And, we have this framework that I mentioned that enables the additional supplemental data if folks have it. So things like pumping schedules, things like that. Now, I think I want to just lend a caveat right off the bat, which is the more flexible model framework is really exciting. But coming out of this working group, I think we want to establish, just like we always have, essentially, this is the formulation of the model. These are the variables that have been tested and validated. And so if you're using this model in practice, and you're saying we're using, OpenEEmeter 4.1 or whatever this is going to end up being, that you are using the model, including the restrictions on where it's been tested and validated. So the more flexible framework that we have that Travis will demonstrate, that's available to everyone. Use it at your own liking. But we do want to say, it's not appropriate to go say, hey, we're using OpenEEmeter 4.1 or whatever this version is going to be, and to market it as such, while you're also incorporating variables that have not been tested or validated in any way through this working group. So just want to lend that caveat right here. Okay, we can go to the next slide. All right, so we've just got some goals, and the goals are finalize this hourly model and make it compatible with the new API. So Travis, Jason, Chulak over at Recurve has put in just an enormous amount of work in not only doing the model R&D, but also revamping how the model is called, creating this new API, and modeling it after scikit-learn. So we want for any of these models to be able to be called in a very simple and consistent framework. So whether you're modeling using the daily model or the hourly model or a new version or an old version, you should be able to use a very simple model and predict type of functionality that is analogous to how scikit-learn has structured their library. So we're in the midst of that right now. We're kind of building ahead on the repository front. And when we finalize the new hourly model, we should just be able to plug it into that framework. So it should be pretty seamless. And so one of our goals is to check that implementation consistency. And then finally, like I mentioned, we're also finalizing this hourly model itself. And that means tuning these hyperparameters, making sure that we're translating this R&D code into the final, public-facing open source repository and ensuring that that translation happens successfully and is well tested. And that involves, of course, debugging. Anybody who's done a project this big with as many lines of code as this has should expect that there will be bugs that crop up and they're found through testing. So we'd also say to any of you who are using this model that if you're finding issues with the API or you're finding any bugs in the code, please let us know, because this is really how this should work. It's not just us, it's everybody using this and finding issues and creating PRs and things like that. So, okay, we can go to the next slide. So, I think I covered most of this, but this is what we're striving for. We're striving for like a very consistent, user-friendly repository with models that are sophisticated and that we can be proud of and we can trust. So with that being said, I think, Travis, I'll pass it on to you. And I believe you're going to dive in first to the topic of interpolation.
Indeed. And one thing I wanted to note from this slide is that part of this model fit and the data structure is that you can put the data in a normal format, and the data will itself, the data class itself, will extract all the features necessary so that a lot of the detailed work that we're going through right now will be very, very easy for the user to actually utilize all of that. Speaking of which, one of those things is interpolation, which sounds like a very easy topic, but then we get into the gory details, and it's a little bit more complex than that. So to start with, OpenEEmeter 3.0 or the Caltrack 2.0 model, the way that its output works is that it is based upon each individual hour, and indeed the input is also based upon individual hours. Now with the new model, its input is actually and its output are 24 hours at a time. And this is critical because this means that each day must have complete features. When I say features, I am referring to both time series and categorical features. Time series being the one that it's most likely to be missing here. And when I'm talking about time series features, the first one that comes to mind is temperature, second is observed. Basically, we cannot have any missing data in that time period for fitting the model, which means if we do have missing data, it needs to be interpolated so that we have a reasonable guess during that time period. Just to give you an example of what I'm talking about here, I am showing one day with, on the y-axis is energy or energy consumed, and I have two missing data points here, both of which need to be filled in, because otherwise, if you were to input this into the hourly model or the new hourly model, it would break. And of course, if you're fitting this in, we would want to fit them in a reasonable place, such as I have put the points here. But the big question is, how do we go about doing that? Because it's not always clear whenever you have multiple missing hours and perhaps the hourly usage. If you were to strictly interpolate based off of the time series, you're always going to basically create a flat line in between the missing points. But this ends up missing a lot of the features that are going to be, when I say features, I'm talking about the shape of the of whatever variable you're looking at. You're going to be missing a lot of that that is going to be similar throughout days as well. So that dives into a little bit of the complexity that I'm talking about. So first of all, what I just described, time series, would be a univariate interpolation. Then there's also multivariate interpolation, where we're taking into consideration different days, not just interpolating between point A and B. There's also different kinds of interpolation, linear, cubic, nearest data, and quite a few others. What we have currently decided upon, this is still a bit of a work in progress. It's not we want to make it as good as possible because this does affect the model, but it's also not a highly critical component. Mostly this is about computation time. But the one that we have decided upon right now is a multivariate RBF interpolator. RBF here stands for radial basis function. And what it does right now is it looks at 7 days prior, so the same day, but the week prior, the day before, the day after, and then 7 days after. And we will fit our data based upon the available data for all of these things and interpolate from the NANDs. Just to give you an idea of what I'm talking about, let's go back to my example where I am showing energy on the Y and the same 24-hour day. And we want to fit these points. Well, in this example, I'm not going to show all of the points that we're looking at because it'd be a little bit too crowded. So I'm just going to focus on the ones that really matter. So for energy, let's look at 7 days before. You can see similar features. So for example, at 6 a.m., we have a spike the week before, just as we have a spike in the day of. We have a bit of a rise in usage, although this 1 hour is different. This is to be expected because our data is very, very noisy. So ultimately, we are just looking for the best that we can do with interpolation. It's not going to be perfect. And then here at the end, it's mostly a smooth curve, more or less. Now, 7 days after, again, we're also seeing that same spike in the morning. And here we're missing a lot of the noise during the day. Perhaps they just didn't go to school that day, if this is a school, for example. And then we still see a rather smooth amount of data over here. So if we use this plus data that I'm not showing from the day before and the day after, we can interpolate these red points right here. And this is, as you can see, a bit more than just a direct time series interpolation. This one has a bit of a rise in it, and this one has more of a curve to it as opposed to a straight linear function. Now, we can do the same thing with temperature, where temperature is going to be much more sensitive to the day before, the day of, and the day after. So if we look at the day before, we can get a general idea of what the temperature looks like. Same thing for the day after. The general shape of the day after looks a lot more similar. And we can use all of this information in order to interpolate our 2 points here. So this pretty much sums up our current interpolation scheme, at least at a high level. There are many more intricacies. For example, what happens if we're missing an entire day? What happens if we're missing 2 data points in a row? What happens if we're missing the week prior, that data point? So there's many edge cases here that I'm kind of glossing over. But are there any questions? Or does anybody have a better idea on how we might approach this?
A couple comments, Travis. Thanks for queuing that up. Let me start with the easy one, which is temperature. I think I've seen pretty commonly temperature just done as linear interpolation over an hour or two because it's pretty safe in most places. You know, obviously there's outlier cases where you've got an adjacent shading object, and so you have a very nonlinear behavior, and like you could see even within the data that you're showing that there's like some periods where you're at an inflection point, and so that's not going to be perfect. I don't know that like the weather of a week before necessarily has a lot to do with it. I mean, actually you're a day before and a day after, so like that might bring some advantage. My bigger concern is with the interpolation with the energy data going a week before and a week after, which I understand why it's a week and not a day. I guess I'm just curious. I mean, clearly there's something going on here in the model that you're feeding the data into that requires us to have complete data sets, but it feels like we're basically overrepresenting the points that we're using to fill with. Is there, can you explain a little more about why we can't just leave those points as null and just not include them in the model rather than letting other hours vote twice?
So for your first question, all of these are using the same data. A week prior, the day before, day of, day after, 7 weeks, or sorry, not 7 weeks, 7 days after. So yes, with temperature, it's going to be much more locally important as to doing that interpolation. But the reason why we are using the 7 days prior and the 7 days after, particularly with the energy, is because a lot of times the data that we're looking at is repetitive in some way. And we have to account for the possibility of having 0 data in this entire day. And the best that we can really do at that point is to say, okay, we're trying to understand the general shape from the week before and the week after. The reason why we're looking at 2 data points there is because of the noise. And then we can use kind of the days surrounding it in order to figure out how do we scale that appropriately for the week of.
But so I still have the question of why can't we just leave missing data as missing data and let the model find the relationships on the data that we really do have?
Because the model quite literally will break if you provide it with null data. So we have to have something to feed into it.
And one more thing, we can remove those days that we actually have null points, totally remove that day, and then predict on the other ones. But it's still, if you want to predict on those days that you have nulls, you need to have complete data set.
Sorry, what do you, so if I took June 4th out of the model, that means when I did a prediction on a future year that it would have nulls for June 4th?
No, you need to have complete set of input to predict for the next June.
But if you did remove it, then you would not be able to predict on June 4th the next year. Because remember, the way that this model works is not entirely based off of temperature. It is the linear relationship between all of the categorical features and temperature in order to best predict the observed. So if you're missing some of that data, then basically the coefficient that would describe that particular interaction is going to be missing.
But I mean, so what if we never have a day in June that's a Tuesday where 3 o'clock is 72 degrees? Then we can never predict if we get a Tuesday in June at 3 o'clock at 72 degrees?
Yes, we can. I think it was a little bit misunderstanding here. So if you don't have June 4th, for example, just June 4th, you can be able to predict it in the next year because it's dependent on the month rather than day of the year.
Okay.
Yeah.
I think it might help to go back to the rationale for using matrices of 24 data points instead of each hour independently in the model itself.
I'm going to defer to Armin to explain the details of why this is necessary. I will say that whenever I was trying to use the model with real data, messy data, missing points. It was consistently crashing.
Which makes sense. Because, okay, so let me explain from the beginning. For the Caltrack 2.0, or the current model that we have, each point has its own, each hour has its own inputs, and then we predict for that the same one. If we don't have it, we remove it. But right now, we look at each day and map each day feature to each day observed values. So if we have a couple of missing data, which honestly barely happens, not barely, but it's kind of, let's say 5% of the data. And then we interpolate that so we can have the data and then map it. And at the end of the prediction, we have a column that says this row is interpolated. So your main data set that you inputted will have the same timestamps predictions. But with the fact that we say, oh, if this row is interpolated or not. So you're not going to lose your data, or we don't add anything to your data. That's kind of a proxy step that we interpolate, use everything so we have a clean data set. And then when we output it, we give you the same data set that you have with another extra column of predictions.
And, okay, so Armin, help us. Let's scratch a little further beneath the surface here. Why is it that we've formulated the elastic net? I mean, I'm thinking about the performance of the model here.
Yeah.
Why is it that we've formulated the elastic net to use these, 24-hour data point matrices instead of just taking every hour independently?
Okay, sure. So if you remember way back in a couple of meetings before, we compared these two methodologies. Basically, the model itself was ElasticNet. One path we could take was, okay, exactly the same thing as Caltrack 2.0. We let's predict for each hour. We have a couple of features for each hour, predict for this one, and then go to the next hour and all the way. Another approach was actually look at each day of features and then predict for each day and then go each day. 1 day at a time. The test error for the second approach, which is the current model, was way better compared to the first one. Why? And the main reason is that in this case, we have a matrix of coefficients rather than having a vector of coefficients compared to the time that we want to predict 1 point at a time. And this matrix can actually extract the time series dependencies between each hour within the matrix. It's faster too, it's more accurate because these relationship between these. So look at each day, predict each day, rather than look at each point, predict each point.
So I think that's kind of the foundation for this decision. It's very simply put that when you put in days worth of data as these matrices, then you're able to get some relationship between the time series data that you basically don't access when you're simply putting in 1 hour at a time totally independently. And so given that and the results of all the testing that these guys have done that shows that approach dramatically reduces error, it is really desirable to go that direction. Now, since we've gone that direction, you then need to have complete feature sets. You can't have these null values.
So is there a threshold where you throw out a day if there's only 1 hour and you're going to interpolate 23? I mean, where's the, like, interpolating 1 hour doesn't stress me out very much, but where's the threshold?
Right now, Ethan, we're leaving it at, but this is something that we need to test. We're leaving it at the same data sufficiency requirements of Caltrack 2.0, which in our minds, we actually hope we can relax these a little bit. If folks remember, Caltrack 2.0 is formulated such that every single month has an independent model. And because of that, the data sufficiency requirements are very, very strict on Caltrack 2.0. If I remember right, it's every single month of the year has to have at least 90% of all hours present in the data set. So, that's a very rigorous requirement, and we feel like it's probably overkill. We, at the very least, I think, need to get back and kind of reformulate the data sufficiency requirements to actually, because this is a totally different approach. Some things are going to be, I think we're going to be able to relax some of those things. But we need to pay attention to this very specifically. And so we haven't had a chance to test that yet, but we're, utilizing what we believe is a pretty overly conservative approach at this point. And when we have a chance to get back and test some of the data sufficiency requirements, hopefully we'll be able to actually keep this in mind and relax those at that point.
Okay. Thanks.
Armin, perhaps I had a misunderstanding before. So basically, if we are missing 1 hour, we can remove the entire day and it will work perfectly fine. And I was not doing that, so that was my mistake.
We can implement it, but because we're having that interpolation and we don't have any threshold to remove them, right now we just relax them and then use everything. But if there's a threshold, we can just cut out that and then train the model and then predict it.
Okay. Mustafa, did you have a question?
Yes, thank you. I guess I didn't understand that kind of requirement to have all of the kind of hours in terms of the features to be implemented. Why we don't simply remove that day if there is a missing kind of hours there and go with that day instead of having the kind of my concern is the IPMVP requirement. So if you look at the option C, in order to calculate the savings, we need a meter data. So you have the baseline model based on the estimation for the consumption. And then for the predictions, we have the meter data. So this is not completely adhere to the IPMVP option C calculation when we need the kind of actual meter data in order to calculate the savings. For the temperature, my question is, there are possibilities to get the data out of the other weather station, like a close by a station that may have the temperature available. For example, what we have seen in Canada, at least in some space, we have something about 30-degree difference between 1 hour to the another hour. And this is completely different from the previous day or the day after that. So having that like a 7 days rolling window, that may impose a significant error to the prediction.
I can comment on the first question, Travis, if you want. So
go ahead.
If we don't have any, for example, a couple of missing data points for example, for the reporting year, we have a couple of missing points, but while we wanted to predict, we need that complete set. We need that interpolation or the proxy step. And then after the prediction has been placed, we remove those interpolated rows. So whatever we get that we have actual meter data, we will get the same row predicted. So basically, we just use extra data to predict it. Same thing in the baseline when we're training it. Basically, we can either remove them based on the threshold or whatever we come up with it, or we can hold them, train it, and then again remove it. So basically, we don't use them. We don't add extra data to your data point to your data set. We just expand and then compress. It's just like a little bit of expansion and compression, and we don't change anything else in the main data set.
I think one of the things that would help here is to show the results of the testing that you have done, Armin, because you've tested this and you've shown that it's very, very accurate. Like what we've done is to randomly remove data points from the baseline period and then look at the data points that get interpolated. But of course, we have the actual data, so we can interpolate those data points, compare them to the actual observed data, and we can see how accurate is this approach. And we can start to stress test things in different ways, like if you remove X number of points at a time, like that kind of thing. So we have some results that I think probably next time we should actually share. And it's important that, I think we have done that testing. It's important that we're able to share it and, demonstrate that, hey, this is actually reliable.
I tested on 400 points missing all the way to 4,000 points missing for a year. And the results are reliable. So I can go back and actually bring that in for the interpolation.
For how many buildings?
Just for one, because temperature
Okay.
is basically the same for all of them.
So back to Adam's comments, kind of my concern is that method may be a good fit for one building or one type of the building. And then when you expand it to a significant number of the building, the result may be different.
Yeah, I do agree with that. If we're going to implement an interpolation procedure, we have to test it on more than one building.
Most certainly. Okay. I'll move on. All right. Supplemental data, and I expect to have more conversation here. In OpenEEmeter 3.0 or Caltrack 2.0, the inputs are temperature, time of week, month, and usage, though all of the last three are pulled out by the date time. For the new model, we have the same inputs with the additional requirement of solar irradiance. And I would note here that we actually have two new models, one of which is a non-solar model and one of which is a solar model. For the non-solar model, it would have the same inputs as OpenEEmeter 3.0. We'll discuss that a little bit more, but basically, same framework as we currently have, just non-solar. Now, we also have the ability, as we briefly discussed last time, to have this new input type where we have supplemental data. And for our data set, we need a significant amount of data. And we ran into a bit of an issue with commercial data in particular, because we have to go back to prior to COVID, because we need as static a data set as possible. So we need 3 years prior to COVID. And in all of our data sets, we have rather limited number of commercial buildings where they have solar PV installed throughout that entire period. So we decided to try to add in this new supplemental data of the solar PV installation date as a way for us to be able to better model these buildings that only have a partial amount of solar PV in the baseline period. Now, when I say solar installation data as a supplemental data, the way that it's actually being added is as 0 and 1. So 0 when there was no solar PV, this is done hourly, and then 1 from the solar PV installation date onward. And that solar PV installation date comes from a number of places. It can be given to us by the utility company, or we can try to detect that by, for example, searching for the first negative read. It's not perfect. We're not saying that it is, and we're also not saying that this is the way that it should be done going forward. We're just trying to make the best use out of our data set that we can. So here is an example of what I'm talking about. Here is 1 year with a meter in which, of course, we have energy versus time, 8760. So this is per hour. And here on November 9th, 2019, the PV was installed. Perhaps they were doing testing prior, which is why it changed from having slightly above to strictly at 0 before then. But regardless, this is when we really start to see power being produced. So we can look at this and we immediately know that this is happening in the winter, as we are in the latter half of the 8760, assuming that we start in January. Now we can make a load shape of this. This is the hour, the seasonal hour of week load shape, where the first group here is the shoulder, the second is summer, and the third is winter. This is 24 times 7, so multiply that by 3, which is how you end up with the 504. Here, we basically see what we just saw before, which is that during the shoulder and the summer, this building was using energy above 0 constantly. However, winter comes around and suddenly we start having these significant dips because now solar PV is installed. Typically, if we were actually measuring this building would be disqualified because it had solar installation during the baseline period. But what could we possibly do with this? Well, we can fit our model to it. And here we're doing a reasonable job at predicting all of its consumption, particularly during the winter where we're seeing these large dips. And then it comes to question, well, what happens if we use this model as is during the reporting period, which is what I have shown here? Well, you would get exactly what you just saw, basically, where it's got some usage during the shoulder and the summer, but this doesn't account for the amount of solar production because, well, when the model was trained, it didn't see that there was any solar produced during shoulder and winter, so it's not going to be able to model and predict that during its counterfactual. Likewise, its PNR-MSE is going to be quite high at 2.5. But if we model that while including that solar PV installation date, we can actually learn from winter and apply that to shoulder and summer. So this is basically saying that the amount of energy produced in the winter is going to be reflected in the shoulder in the summer. Now, keep in mind, this is an extrapolation, and it's obviously under-predicting here. But that's not the point. The point is, how much of an improvement on what we were doing before is it? We're also not arguing that this should not be disqualified. In fact, if we set the same threshold criteria as being 1.4, this should not have been allowed anyways. So right now, as far as PV installation goes, this is not actually viable because the model that it's producing would be above 1.4, which is roughly equivalent to a CVR-MSE of 1. So in many cases, again, disqualified. But for the purposes of us being able to model those commercial buildings in our data set where we have very few and we need to make the most of what we have, this is a significantly better option, which is why we have chosen, for the purposes of hyperparameter optimization, to include this. All right, now, questions. Feel free to eviscerate me. Yes, Mustafa.
Is there any possibility to do it like when you spotted the installation of the PV, develop the baseline regardless of the winter, applied, this is for the baseline, and then apply the same model for the shoulder season, summer plus winter? The difference between them during the baseline probably is the impact of the PV, and then do it as a non-routine adjustment for the reporting period?
then you are also taking into consideration any other changes, and all of that would be lumped in with the change that you're trying to ascribe to the solar PV.
So the way I categorize it, the model, the original model, the baseline model before the installation of the PV should handle all of the independent variables, impact of the independent variable like outdoor air temperature or anything else, except the PV installation. By having that one implemented to the winter, you find out what is the impact of the PV. And then this is just a single line adjustment to the reporting period. Because the original model is able to compensate all of the changes except the installation or except the PV.
But how about the winter? So in the winter, we don't have that kind of relationship, and we don't have kind of the sizing of the PV that we can extrapolate for the shoulder and summer in the reporting here.
That's a good point, Armin. So if you have a complete missing winter, like for example the PV install right at the starting point of the winter season, it's a mixed impact. So that's a very edge case. Let's say you have a bit of winter, the possibility of having a kind of predictions with the original baseline model to predict the winter. And then during the winter, you have the installation for the PV. So the model with the partial winter is able to predict the situation with the winter. Of course, if you have the entire kind of winter impacted by the PV, that's an edge case, that's the extreme case, and that approach is not applicable at all.
Yeah, so that's kind of a point that we need to atomize the whole thing, and it's a little bit hard to just. I think there's the best way to do that is to find the negative, or we have kind of other approaches to find where is actually the regime change in terms of PV solars, but that's for later conversation. We need to have some automation. Okay, this is a PV installation. There's some date, and before that, there's one model. After that, there's another model. It's going to be a little bit hard to just categorize for each meter for each season.
Absolutely. So what I'm explaining is the IPMVP approach when they call it non-routine adjustment. So they consider the installation of the PV as a non-routine events which impacted the entire consumption. And there are about 9 different approaches, right, to address that non-routine events. That simplified kind of explanation I provided is based on almost all of those non-routine adjustment approaches. The one you explained to us today is a different approach, like having the non-routine events as part of the baseline, and then develop the model by including that events, like you call it extrapolation.
I'm not clear on how we would account for shoulder and summer PV production without having information from the reporting period. And if we're including information from the reporting period, then we are now having a conflated issue of, well, now our baseline period is informed by our reporting period. So how do we then judge our reporting period, which is supposed to be independent of our baseline?
I can add one more explanation there. So by subtracting the baseline predictions, this is for the winter, with the actual consumption during the baseline, you have the predictions from the PV generation. Is that correct? So you have the baseline model output minus the actual consumption. The result is the impact of the PV.
we don't have a separate model for PV.
Of course, you
It
don't
is
have
all
it.
one model.
You don't have it. So you have a model from the actual consumption up to the installation of the PV.
Sure.
Okay. That model is predict something during the installation of the PV. And then you have the actual consumption. The difference between
This is
these
still
two values.
Either way is an extrapolation. You're extrapolating a model built on a shoulder in summer into winter doing that.
This is not extrapolation. This is a
Yeah.
prediction minus the actual consumption.
Yeah, but Mustafa, imagine we have these are non-participants. But if we have a participant, that difference between the actual data, actual AMI versus the model based on the baseline, then it has PV impact and the project impact.
Yes.
So that would be a mix
Yeah.
of that.
So in that case, you need some information about the installation date for those projects. You need some information about the installation date for the PV in order to separate them.
Yeah, I mean, I think I definitely understand what you're saying with respect to, like, let's say that you take this example, the baseline period begins, say, March 1st, and then the customer gets solar PV installed in November 1st, which we call a winter month. So then you have November, December, January, February, in which the customer has solar installed, and it is still the baseline period. So we're just purely talking about the baseline period. Now you can take the model that you developed from March 1st through October 31st, and you can say, okay, this is our model. And now we're going to project that model forward into the winter time period. And we're going to take the difference between that projection and the actual observed data as the impact of the solar PV panels themselves. I think in the absence of, anything better, that might be just fine. But I think Travis's point is a good one, that we don't trust that a model developed in only 8 months of the year without any of the coldest months, as an example, is valid to project into the coldest months of the year. We don't know. We don't have any observed data likely at that point to say this is how this building behaves when it's 10 degrees or 15 degrees, because at that point, who knows, maybe the coldest day in the spring, in the fall, and in the summer was 30 degrees. Who knows? So I think like that, your approach, I think, is logical, but it's not without issues. So I mean, anytime we're looking at something like this, you have to sort of choose the lesser evil kind of thing. And yeah, maybe what you're describing is a lesser evil. I think what we would like to do with this is test how much data needs to be available in the baseline period when the building has entered a new state of operation in order to actually have a valid model. And we'd like to come back to the group with some recommendations on that front based on the analysis itself. We have a bunch of meters where there are varying time periods in the baseline period with solar installed, but not the entirety of the baseline period. So how much data is actually needed in the baseline period to consider a model valid when there was that fundamental change of the PV installation?
I totally agree. I totally agree with that one, and I'm gonna reverse that kind of issue to the same extrapolations. If the level of the data impacted by the PV is very tiny piece and you wanted to extrapolate that one to the entire reporting period, the same issue happened there.
Oh, I totally agree, which is exactly why I'm saying, if you only have a week, let's just say, just hypothetically, you only have a week in the baseline period where the customer had solar PV, the very last week of the baseline period, the customer got solar PV. I'd be pretty surprised if that one single week was enough to create a model that we should trust in the reporting period. So, but what I don't know is, should it be 3 months? Should it be 4 months? Should it be 5, 6, 7 months? How much is actually needed? And the good news is that we have data on a whole bunch of customers that had solar PV installed at some random point in the baseline period, some very early, some very late. So we should be able to analyze these results now that we have them. And like I said, come back to the group and say, hey, here's what we're seeing. And I think that if we do that, I'd like for us to do that in the coming weeks here. If we can do that and come back to the group, then I think we can have a much more informed discussion on the limitations of this kind of approach.
But I would like to pull back, because all the discussion right now is talking about this as savings. We're not saying this is for savings. What we are doing is trying to maximize the amount of data that we can test our new model on by saying, yes, we are going to also test on this. It's 30% better than what it was before, but even if it's absolutely terrible, that's okay as well, because we have an outlier rejection scheme for our objective function so that we can toss out absolute trash. So we are not suggesting that this be done for savings. This is just for creating our model and maximizing the amount of data that we have for our model. With that in mind, I'm going to close.
It's a good point, Travis, and I would add to that we do want to, there's a lot of cases where people get solar PV installed in the baseline period, and there's a lot of meters that get thrown out for poor model fit and other issues. We want to be able to maximize the applicability of these models. And so I think that this approach is really, really promising. And Travis, Armin, I guarantee you that you did not add the flexibility to add these kinds of flag vectors, to the inputs without thinking about the savings case. I promise you that.
Yes.
So it's good. This is really, really exciting. And Mustafa, like what you're talking about and taking the conversation into the prospect of like, can we use this and can we measure savings with this? Yeah, we're super interested in that. But we just need to test it some more and come back to the group. And then I think we'd be really open to what people's feedback are at that point. But for right now, yeah, I think we're just trying to, like Travis said, we've gone down this road because as everybody's very familiar with, data sets are super limited. We're working with what we have, and we need to maximize the data resource that we have here.
Okay, so I'll close off the discussion.
One more question, Travis. So if the PV put in place somewhere in winter, and then and that is a temporary kind of installation. So for example, during the summer or during the winter the next year, you call it reporting period, something happened with the generation of that PV. So how you distinguish between the model predicted by using the PV constantly running and something happened with the PV operation during the reporting period?
We're going to pick all that stuff up. And I would say, you could kind of also say, well, look, what happens when somebody has a kid go off to college halfway through the reporting year? There's all sorts of changes in building consumption and building state. Sometimes we can detect those things, sometimes we can't. But I guarantee you that every single person on this call right now had some way that they changed energy consumption over the course of the last year. We're going to pick that stuff up. This is why we rely on population level statistics. I want to be really clear. We would never come to a meeting like this and say, we recommend the usage of these models on individual buildings for individual building savings results that you should run settlement on. We rely on using these models consistently across large groups of customers where where usually what you see is highly symmetric distributions of changes in year-over-year energy consumption. And on top of that, we also recommend the use of comparison groups. And we can talk more about that as we go. So for both internal model error and external factors, global pandemics happen, right? So these kinds of things are contextual, issues that if you're going to use some model, or if your task is to take one single building and make a highly accurate measure of the savings from participation in a demand side program, then you better be paying attention to a whole bunch of other stuff that is not appropriate to include in a model that's meant to be run symmetrically on hundreds of thousands or millions of meters.
Right. We have to move on. We cannot discuss this anymore. There are many more slides. Moving on. I apologize. On to the hyperparameter optimization. So here's the problem setup. We have a loss function, and we have mean squared error. And then this is a general description, by the way, of an elastic net. And then we have some penalization on the coefficients based on certain parameters. There are two ways that we can penalize these coefficients. We can penalize it with an L1 or an L2. L1 is called a lasso regression. L2 is a ridge regression. What is the difference here? L1 is looking at the absolute value, whereas L2 is looking at the squared. Now, with an elastic net, these two values, they are done by a ratio, which is called the L1 ratio. And if the L1 ratio is 1, then it is entirely a lasso regression. If it is 0, then it would be a ridge regression. Anywhere in between, it's an elastic net. But the strength at which we penalize these things is done at alpha. So these two variables are the ones that we care about. And I suppose I should have showed the formula here. The total thing that we are minimizing is the mean squared error, which is all of the residuals, plus this alpha value, which is the strength of penalizing the coefficients, plus the norm of those values. For reference, if you're unfamiliar with an elastic net, ridge regression, lasso regression, what this effectively does, if you are doing an L1 penalization, an L1 it's a feature selection method, so it pushes all of your coefficients towards 0 if it can. Of course, it's balanced out by the mean squared error, so it's not going to push them to everything to 0 unless your alpha is very, very high. An L2, on the other hand, is trying to reduce the square. So the square, what that's doing is that's effectively pulling all of your coefficients together as opposed to down. Okay, those are the two values that we are trying to optimize in this hyperparameter optimization. Now, the data that we used are 16 subsamples with 250 IDs each. And each of these IDs has 12 k-folds. Or not 12 k-folds, it has 12 folds. And here, when I'm referring to a fold, I am referring to prior presentations where I showed that rolling window. So basically, this is one starts in January of 2017, and then its reporting period is in January of 2018. The next fold would be February, so forth for 1 year. The purpose of this is to try to reduce the amount of noise that we're going to be seeing for each of these. Because as we all know, crazy events happen, so how can we make a model that is going to be good in general if we are highly influenced by those events? Now, the next thing is that 8 of those subsamples is residential, and 8 of them is commercial. This is done we obviously have much more residential data than we have commercial, but we need to balance residential and commercial so that the model is equally good on both. Again, half of each of those, so half of residential and half of commercial, is solar and half of them is non-solar. The purpose here is to make it so that if you are running the solar model, it does not matter if you are using residential, commercial, solar, or non-solar. the answer that you will get out will still be good. The algorithm that we are using to optimize this is, at least a couple of years ago, it was the best open source global optimization method that you could find, or one of the best, and that is RBF opt. RBF here being radial basis function, opt being optimization. Now the objective function. If anybody ever shows you an optimization and they don't talk about the objective function, you can ignore them. They didn't do anything. Our objective function is the average of each of these folds test RMSE with doing an outlier rejection on the entire population of test PNRMSE that we have. The reason why this is very, very necessary is because if you guys remember from, I think it was 1 or 2 presentations ago, we had one subsample that was just way out there. When we optimized for the subsample itself, the coefficients that we were getting were very, very different from every other subsample. And then when Armin looked into it further, he found that the reason why that one was different was actually being influenced by just, I think, 2 of the folds. So those 2 folds can be highly, highly influential. So we're using an outlier rejection to get rid of those and then taking the average. Before I jump into the results, which is the next slide, are there any questions about how we have set this up or concerns? Okay, moving on. So here's what we've got. This is tested on 4,000 modeled meters. This is the solar model. And we found that we have pretty stable hyperparameters. And remember that each one of these little points that I'm showing you is the average PNRMSE with outlier rejection on the 4,000 modeled meters times the 12 rolling periods. So this is a lot of data inside of each one of these little data points. And this is the result of the optimization. So here we have the log of the alpha. The reason why it needed to be the log is because we're talking about many orders of magnitude here. And alpha it's entirely reasonable for alpha to vary by many orders of magnitude. So we needed to test them all. Whereas percent lasso can only go between 0 and 1. And the z-axis here is, of course, our mean PNRMSE. So the first thing that you're going to see is quite clear that we're looking at a pretty well-behaved response surface, which is fantastic for us. If we were looking at a response surface that was very, very noisy and had many local wells, we would have an issue. But that's not the case. Instead, we see that we've got one valley straight down the middle between approximately -2 and -1 of log of alpha. And then if we look at the projection coming from this direction right here of mean PNRMSE on the y-axis now and percent lasso on the x, you can see that we're relatively insensitive to the percent lasso. So I'd say that we really want to avoid going below probably 0.3, and we kind of want to avoid going above 0.7 or so. Anywhere in here is pretty low, and it's going to be basically more or less the same mean PNRMSE, which again for us is fantastic because this means that our hyperparameters are going to be pretty accurate for this and hopefully any other solar meters that we put in. Let's look at some different projections though. So if we look at that projection from head on, just in case you were doubting that this does have just a valley V shape to it, this is the projection straight on. So looking at log of alpha on X and the mean PNRMSE on Y. And again, doesn't really matter what the percent lasso is. Like it all appears that the minimum is going to be roughly around -2 to -1. Now, if we look at an overhead of this, here, log of alpha is on Y, percent lasso is on X, and the color designates the mean PNRMSE. You can see that we, again, do have that nice little valley. Most of our testing was done in this region, which makes sense, or the optimization method chose to test mostly in this region as it's searching for the minimum. But we do also have a reasonable number of points exploring the entire surface, so we're pretty safe in assuming that we have found the approximate shape of this response surface. Now, let's talk about the non-solar model. And this is going to look really familiar. Again, very good news for us. The difference here is that one, the mean PNRMSE is higher for the non-solar model on the high end here. And also, this rise on this side of it is not nearly as high. But otherwise, remember I just mentioned that the ideal log alpha for the solar model was between -2 and -1. Guess what? Same thing for the non-solar model. And I'll skip showing the projections and I'll just show the overhead view. So for the overhead view, same thing. We have a valley straight through the middle of where it really matters what the log of alpha is, but it doesn't really matter what the percent lasso is. It searched the primary area between 0.2 and 0.8, so we can be pretty rest assured that the minimum does exist within this area. So this, oh, I thought I had more information here. Oh, okay. So for the hyperparameter optimization, let's look at the two overheads. And I cannot tell you how pleased I am with these results, because this tells me, so the solar model, remember, has all of those variables of Caltrac 2.0 plus GHI plus that solar installation date. So it's got two additional columns of information compared to the non-solar model. Yet despite that, we have almost the same response surface, almost the same exact minimum, which I've shown here in the red dots. By the way, I meant to put it here. The optimum alpha, I believe for the solar model was 0.032, and for the non-solar model was 0.032. So it's, again, that's what we expect for the log we're talking about. Sorry?
0.032 and 0.037.
Exactly.
Yes, and that's so close to each other, which means that we could almost use the same model. In fact, we might even just do that for the solar and the non-solar model, considering that the coefficients end up being almost exactly the same. The difference is really where it finds the percent lasso. But the reason why I showed you that projection was to show you how insensitive we are to percent lasso. So for the non-solar model, it found the ideal as being about 0.6, whereas the solar model is about like 0.5-ish. We could cut the difference there, and we would get almost the same result because we are insensitive to it. Okay, any questions? Shouts of excitement? I'll take any.
Good stuff. Good stuff.
All right. Oh, thank you, Ethan. You have no idea how much Matplotlib does not want to make plots like these. It took me forever. These are contour plots, and in Matplotlib, it always wants to plot the contour lines, so erasing that was tough. All right. So, we still have time. This is all optimization results, but I remember I told you that these individual points here, there's a lot of data in there. So we really need to investigate what that point is so that we can better understand our model, start to try to find any deficiencies, and then if we find them, start thinking about how we can tweak the model in order to arrive at the best possible final model. So let's zoom into those two data points and talk about population results. So starting with the non-solar model, this is res and commercial. We found a 1.5% error improvement, which by my estimation is a fantastic improvement considering we weren't trying to improve the non-solar model at all. Starting on the left here is Caltrac 2.0. On the Y are counts, and on the X is the PNRMSE of each of those folds that I was talking about earlier. Here, these dotted lines are the means of each of these. So the blue is the baseline, and the orange is the reporting. The blue's mean PNRMSE is 0.84, and its reporting is 1.13. For our new model, we have a worse baseline model. You could say worse, but I'd say less overfit, as the error is 0.94 and the reporting period is 0.12. So what does this mean? This means that our error in the testing period is slightly better, and our baseline error is slightly more reflective of our true test period. And so then we can just basically take the division of these two, and we can figure out how overfit we are. So for the Caltrack 2.0, you come up with about 1.35, whereas with the new model, you have 1.18. So with the non-solar model, we have a tiny, tiny incremental improvement in error. I wouldn't even say that it like 1.5% could be with an error. Who knows? It's perfectly fine, but it's a lot faster and it's less overfit. So ultimately, that's going to save us money whenever we're running this model, and whenever we are estimating our uncertainty based on the baseline period, that's going to be a lot more accurate with the new model as opposed to Caltrack 2.0. So I say this is a net win. With the solar model, we see more significant improvement. We see a 6% error improvement. And remember here, I'm not actually focusing yet on the time periods where solar is really going to matter. This is just overall. This is including nighttime, everything. So here, again, much the same as we saw before, where the baseline is slightly worse, less overfit, and the reporting period is the error is actually better. Key things to take away from this is, what does this actually mean? It means that we have more data towards the left, lower PNR-MSE. You can see here on this side, that's all being pushed to the right, whereas with the new model, that is doing a pretty decent job of approximating the baseline period. And as far as the overfit goes, again, we're seeing a pretty significant improvement from 1.45 to 1.29. If we want to dive into one of these, since this is including both residential and commercial, I'll show the one that we have more improvement in, and that is with commercial. So with commercial, we're seeing a 7.25% error improvement. Again, I really want to emphasize, this is talking about over the entire year. This is not even focusing on the time periods where it really matters, because most of the time, it's roughly about the same answer. But in the time that matters, we're seeing a lot of improvement. Other than that, again, mostly the same takeaways. We're less overfit, and we have quite a lot. Our reporting period is further to the left and more reflective of the baseline than before. So this is, I guess, phase one of our population results. Are there any questions? Okay. And then I will pass it off to Adam, who was doing some of his own work and looking at what it looks like in those time periods that we really want to see improvement.
Thanks, Travis. Yeah, every now and then I still get to dig in, which is amazing. And I had a chance yesterday to kind of poke around at some of this. And what you've seen some graphs that are like this throughout the course of the working group. And I just kind of reformulated this a bit. So let me take a step back and just explain what we're looking at here. So for solar, the main objective, or one of the main objectives, we wouldn't be here today if it wasn't for the desire to improve the performance and the reliability of the OpenEEmeter for solar PV customers. Now, when would we actually expect to see issues arise in Caltrack 2.0? Well, when the sun is shining, right? Or when it's cloudy. So in the middle of the day when you actually have solar irradiance. I wouldn't expect that, the Caltrack 2.0 time of week and temperature model is going to run into major issues at 1 a.m. when there's no solar irradiance. The issues start to arise when you have 1 month in the baseline period, or 1 day, or whatever it is, that is very sunny, and then the corresponding day is very cloudy in the reporting period, or vice versa. So what we're taking a look at here is these are both the test data sets. So these are the reporting periods. And on the x-axis, we're plotting the difference between clear sky solar irradiance and the actual solar irradiance, inclusive of cloud cover and fog and all that other kind of stuff. So we've binned data points here. This is a residential sample. We've just binned data points according to this metric on the x-axis. And then on the y-axis, we're looking at the average hourly model residual. And I'm specifically focused only on hours that have solar irradiance. So we're ignoring all the 1 a.m.s, the 2 a.m.s, the nighttime kind of stuff. And if we look at the graph on the left, the green circles are the Caltrac 2.0 model, the red squares are the new model, and like I said, residual is on the y-axis. And if you really stare at this closely, you can see that on the far left side of that plot, the Caltrac 2.0 model is over predicting on hours where there is no difference, between the clear sky GHI and the actual GHI, meaning that those are very, by and large, they're very sunny hours. But for hours where there's a large difference between the clear sky GHI and the GHI, then we're starting to see a real bifurcation in how the model is performing. Well, we're actually seeing that at 0 on that metric as well, because the Caltrac 2.0 model is basically trying to split the difference between all the hours it was trained on where it was sunny and all the hours it was trained on where it was cloudy. But the elastic net model, because in large part, because we've incorporated solar irradiance now, it doesn't have to try to split that difference. It can actually use solar irradiance as a variable. So we're seeing dramatic improvement, especially when we get these really cloudy days that are represented by data points further on the right of the graph. Now, these are residential customers. For those familiar with, consumption patterns, we're starting to see that when the days are roughly, say, 30% cloudy to 50% cloudy, we're seeing more than a kilowatt hour of residual in Caltrac 2.0. That's, you might ask, well, how much is that relative to a total building's actual usage? Well, normalizing is difficult here because when you try to normalize a solar PV customer, you have somebody who has negative consumption part of the time, positive consumption part of the time, and without being able to disaggregate the actual building consumption, what are you going to normalize by? You're going to end up normalizing by a value that's actually very close to 0. So I've taken normalization here, and I've focused that exclusively on hours where the clear sky GHI is 0. So in other words, hours like nighttime hours, basically. Any time where the sun just is not shining. And I'm taking the average building consumption during those hours. And so we can see that, the error in the Caltrac 2.0 model is amounting to about 60, 65, 50, depending on where exactly you are, anywhere from, if you're above, say, 25% cloudy, you've got error of more than 30% relative to what the building would be using in a nighttime hour. And when you get even higher up to like 50% cloudiness, you're talking about, error on the order of more than 65%. And I'm being a little flippant with how I'm talking about this because this metric on the x-axis, this average irradiance difference, this is providing more weight inherently to hours in the middle of the day where there is a high degree of solar irradiance. And I think that that's the right way to be looking at this. Because if you have an hour with, we're seeing that the clear sky GHI reaches a maximum of about 1.0. And that's happening, in the middle of the day, noon, 1 p.m., 2 p.m., when the sun is high in the sky. And when you have those hours, then a difference of just 20%, so from 1.0 to say 0.8, that can drive a greater discrepancy in the Caltrac 2.0 model than you would get by looking at like a 7 a.m. hour where it's actually 50% cloudy, but your actual absolute difference in clear sky GHI versus GHI is much, much smaller because there just isn't that much sun shining at that point. So kind of a convoluted, complex topic, but if all you walk away with from this slide is the new model is achieving the goal that we've really set out, which is dramatically improved performance and reliability during hours where you have a large discrepancy between the data that the model was trained on, which is largely going to be sunny, at least in the data set we're looking at, versus actual cloudy hours in the reporting period. That's one of the main objectives here. And these graphs tell us that we've seen, dramatic improvement across the entire spectrum, including even very sunny days. So hopefully that helps folks get a sense of, why we've done this. When you have these green curves, those green curves essentially represent high risk in using the Caltrac 2.0 model to measure solar PV customers. So with that, Travis, I'll hand it back to you. We can talk next steps here, or we can talk if any folks want to dive into this, happy to discuss this a little bit too. I think we just have a couple minutes.
All right. So next steps. It may not be clear, but we need to do a lot more analysis on these population level results. In fact, we haven't had these very long. We've had some of them since Monday, and some of them finished today. So there's quite a lot more to be done into digging into these. Now, depending on what we find when we dig into these results, I'm particularly interested in changing some of our categorical features into time series to see if we end up with better results, because one advantage of us just tinkering with that PV installation date is we tried it first as a categorical feature and then as a time series. And we found that as a time series, it was much, much more accurate and provided a lot better results. So I'm kind of curious now if we do that with other categorical features, if we also see an improvement. If we're finding out that we need to make some other changes, then we can always re-optimize the hyperparameters now. Now that the code is already in there, it's all set up, it's far easier to do now than it was initially having to create all of that from scratch. And if we're finding that bias is an issue, such as like seasonal bias or any of the biases that you might be concerned about, extreme temperatures, that kind of thing, then we can entertain thoughts on how to resolve that, and maybe splitting the model. I'm not very sure. We'll have to see what we do when we get there. And then this can be done at the same time in parallel. We want to get the hourly model fully into OpenEEmeter. This means we need to put all the guardrails on so that the defaults are for savings calculations, and then there are options to switch it to more of a research mode so you can do whatever you like with the model. We need to do lots of testing. Now, I'm not talking about testing in terms of setting limits on how much data is necessary and all of that. I'm talking about just making sure that this will run all the time, no question at all. With the latter there that I was discussing, we're hoping that that can be another initiative, much like we've had the daily initiative, the hourly initiative. We want to really look back and look at all of the requirements and see if we can make those a little bit more data focused. And then finally, we need to improve our documentation. This includes the backlog documentation of the daily model, but that's going to be a big priority in redoing this next version. So with that, we are done. And if there is any more discussion about anything, including that PV installation date and how to do solar PV customers in the baseline period, I'm happy to entertain it now that we're finished.
Thanks, Travis. Can you just clarify one thing in the slide? So when you talk about changing categorical features to time series, in terms of the PV installation, my understanding was that categorical would mean you had a date associated with some flag that said PV was installed. Time series is you have a vector that's the same length as the same shape really as your energy data with ones and zeros. what are the other categorical features we're talking about, and what would that look like?
So currently, all of our time-related features are all categorical features. So this says whether or not it's Monday, Tuesday, Wednesday, Thursday, Friday. This says whether or not it is January, February, March, April, May. Armin, is there another one that I'm missing, or is it just those two?
No, it's day of the week and month of the year now, which attached to each day time feature. That would be our sample for the day.
Okay.
So basically, I'm wondering what happens now if we have a one hot vector where we say this is January, and it's a time series where it affects each individual hour, as opposed to just appending this is January onto the end of the time series.
Gotcha.
Because effectively, that's what we did with the PV installation date, and it was a marked difference.
So you tried PV installation date either by putting a flag at the end of each 24-hour vector or by adding another 24-hour vector in parallel.
Yes, and the time series, the extra vector was much better.
Okay.
One thing, Travis, real quick. For the PV installation data from categorical to time series, we had 0 and 1. That's why we could just like add time series. I didn't want to deal with the one hot vector of 12.
So I think that if we put that, well, actually, I don't know. It's worth exploring both ways. One would be we just make a single hourly vector where we populate that with 1 through 12, or we can create 12 hot vectors where we just say this is January, this is February, etc. I think the first one is not going to end up in a good place. I think the second one is, my guess is that's the better choice.
I see your point.
I think that's true because if you provide it just, I mean, I would assume you would provide it like an integer. So like January is 1, February is 2, and that kind of thing. Yeah, then like the model's got to latch onto that integer and provide some coefficient on that, right? Whereas, yeah, so I would, yeah, strongly suspect that approach would not work out very well.
Can you trick it with an ABCD that tells it that it's an enum and not a scalar?
It's a good idea.
I don't think so.
I mean, you could just give it the strings of the months, but the model may not be able to just take enums. Anyway, I'll leave that in your hands. I know we're at time. I don't want to bring up these topics. I do still want to chat with you guys about some weird things that I'm seeing working with a very different data set. Actually, mostly we've been working with ResStock data, but because it gives us hourly data, then we can downsample to daily and whatnot. And Travis, I mentioned some of this stuff on over email to you, that there's like various types of issues with like seeing both signs on the heating and cooling slopes, which we expected to only see one sign, and really non-interpretable balance points, right? From 10 to 100F for heating, stuff like that. So I'm still digging into that a little more so I can find some good data examples, but those are still open questions from my perspective for the existing daily models. Definitely looking forward to testing out the hourly models when they're ready, but just wanted to give you an update while we're here that I still haven't totally gotten to the bottom of those, and hopefully I can show you some stuff that might provide some fodder for your future development. Or maybe you can just tell me what I'm doing wrong.
It brings to your concern about the balance points brings to mind a rather an oddity with the daily model. So with the daily model, in order to make it work as one single model where you can reduce it down all the way, I have to also do some strange things with the balance points sometimes. So for example, if you have what is effectively a linear model, then the balance points, depending on which way the model is, whether it's a cooling or a heating model, the balance point will technically be placed because we have no information that the model would continue to go negative either way or would continue on its downward slope. So instead, it's treated as that is the end of our data, therefore that is the balance point. And that extends into what is effectively a temperature-independent cooling or heating temperature-independent model, where that balance point for one end is going to be at the end of the data, and at the or it might be at the what is the true balance point.
So it's basically a what we call in the classical terms like a two-parameter model, just a slope and an intercept.
Yeah. In order to be able to reproduce that, that's what I had to do funny things with the balance points.
Interesting. Okay. I suspect it will look more logical when I see some examples, and maybe that's what we're seeing, and why those don't make sense if it's just the single slope. I mean, the single slope models like aren't great physically meaningful models anyway, but sometimes that's just the best you can do with the data.
Right.
So, okay. Well, anyway, just letting you know, I'm still working on that stuff. So, I don't
Okay.
wanna solve it, but
I look forward
thanks
to it
for
whenever
that.
we're able to meet.
That'll be great.
All right. Well, thank you, everyone. It's been a good meeting, and can't wait to hopefully next meeting I can say that we have a working hourly model, but we'll see.
Awesome. Well, great work. Really appreciate all the visualizations and the information you had to share. Looks very promising.
Yep. All right.
Thanks, Travis.
See you guys.